All right, so today is the last day. So today's the last day, and I'd like to discuss a little bit about the applications of elliptic curves over finite fields to cryptography. So I need to introduce, in case you haven't seen it before, how exactly you set up an elliptic curve crypto system. So here is an example. Yeah?
Monroe asked you to
Zoom in.
Apparently he's watching from his phone.
Auto. All right. Is that better?
He'll tell me in 2 minutes.
All right. So Alice and Bob, chosen for the first letters of their names, wish to communicate using y squared equals x cubed plus 71x squared plus x over f 8,147. Okay, that's a prime field. The point P equals this, has order L equals 2081, which is the largest prime dividing the order of E over this field. Okay, and so Alice and Bob each choose a random number. Ka is Alice's, and KB is Bob's. All right, so Alice does not tell this number to anyone, not to Bob, not to anyone else. Bob, likewise. They are secret. These are the secret keys. And the goal is using these unknown numbers to the other party to compute something common that both people know. And this can be done in simply the multiplicative group, but it's better to do it in elliptic curve. So they first need to compute something public that they can give to other people. So Alice computes PA is her private key random number, which she uses to repeatedly add P to itself enough times within the elliptic curve group. This is her public key now. She sends this to Bob, publishes it, whatever she wants to do. Bob computes, likewise, a multiple of P using his secret number. Because this is related to sort of, like if we were doing it as a multiplicative group, we'd be exponentiating. Here we have an additive structure, so we're doing repeated addition. So just as in exponentiation, you have a base. This is sometimes called a base point. Now, using Bob's, so this ends up being this point, and this ends up being this point. You can get those by Sage or Magma, or you can write your own code to do it. Using Bob's public key, and her secret key, Alice computes, and Bob likewise computes the same thing. He uses Alice's public key and he uses his secret key. And gets the same thing. And so now they have some common information that without knowing the other person's secret key, they can compute say a common key to use in a symmetric algorithm like AES, or there are protocols that would allow them to send a message directly using the public key set up on the elliptic curve. So this is an example we call the discrete logarithm problem because, if you look at the analogy with exponentiation on the multiplicative group over a finite field, you're trying to solve you're trying to get an unknown exponent if you're trying to break the encryption. To break the crypto system, Eve, chosen because she's an eavesdropper, she must solve that or that. So both those points are known to Eve, but n is not. And we're doing this additively, but if we were doing it multiplicatively, this is analogous to solving AX equals B with A and B known and X unknown. Well, if we were working over, say, the real numbers, this would be trivial. We would just break out our logarithm formula and compute as many decimal places as we needed, and we'd be done. And if we were using p-adics, there are, of course, p-adic logarithms. So the question is, why can't you do this sort of thing with elliptic curves over finite fields or with finite fields themselves? I mean, we indeed have effectively, because elliptic curves are basically have a Lie group structure, you can look at, in a sense, a logarithm. And from that perspective, you might approach things with the formal group on elliptic curve, which I didn't have time to add to my notes. But in practice, it would seem that it's not as effective as other methods. So I do want to discuss methods of attacking the problem, but let's just complete this and say that this is called the discrete log problem, or DLP for short. So the ability for this system to work is reliant on the hardness on solving this kind of problem. And if the problem turns out not to be as hard as we expect, then we need to find a different hard problem. The hardness of RSA is based on the hardness of factoring. So in any particular key setup you might want to make, you're basically looking at things that are known not to have, for which no polynomial time algorithm is currently known. The problem can be approached over FP, just if we're setting up the discrete logarithm problem on the multiplicative group FP, not on the curve, that has a sub-exponential algorithm that works against it using sieve methods called index calculus. There are sub-exponential methods of factoring, as we learned, but seemingly the best methods against elliptic curves directly are not as effective as the methods over FP times. And so, for now anyway, it's safer to use elliptic curves from that perspective. But that doesn't mean it'll stay that way. We need to continue checking the systems, and of course with quantum computing looming, it's basically already known that this can be broken in polynomial time with a quantum computer. So but in any particular case, however we might want to set it up, we're basically looking for a hard problem to solve. And so let's do a quick comparison about the hardness of the DLP problem in FP times and in over elliptic curve. Hardness of DLP in that or that. So this table comes from NIST 2016, I think is the latest. NIST is an organization which sets standards. Some of the standards they have are relatively up to date, some need revision, but this table is relatively recent. They occasionally make an effort to revise standards. Okay, so there's AES 128 192, 256. So that's the symmetric algorithm. In order to get a symmetric key to begin with, you first have to establish communication with public key. So the question is, what public key, and so this is in bits, all right? So this is like the number of bits. So for RSA, you would need 3072 bits in order to be able to effectively establish a 128-bit key for AES. Likewise with Diffie-Hellman. And seemingly, this is saying that RSA and Diffie-Hellman are at the same level of difficulty because their numbers, the number of bits required for each, are the same. ECDH, elliptic curve Diffie-Hellman, is much better from this perspective. It is only the double of the number of bits of AES. So it's growing proportionally to the number of bits of AES, whereas the number of bits required by RSA and Diffie-Hellman is growing. And so if you go even higher, the elliptic curve method has an even better benefit. And then SHA, which is a hash algorithm, or SHA-3, is on par with elliptic curve Diffie-Hellman. So if you look at those numbers, it starts to look like it's better to like a lot better to send something with elliptic curves than with RSA and Diffie-Hellman. That's a little bit misleading because the computations for elliptic curves do require more work. And so to really have an apples-to-apples comparison, you need to sort of break down the algorithm efficiencies of each approach. So I'm going to say a little bit more about that. I'm not going to prove any of these for you. Okay, so when I quote algorithm efficiencies, I prefer using the logarithm of the size of the number, essentially the number of bits. It's more telling because when you are plotting times from a computer, like if you run actual tests on a computer, and plot a chart of how it grows when you increase the number of bits, that's exactly what you see, is that if something's growing quadratically in n, then you see a quadratic growth in n in terms of the time. So from this perspective, then, when Teitelbaum showed this, the exponentiation was log x, okay, his x was the number itself, so his log x is my n, okay, but that's the total, he was talking about the total number of steps, and kind of ignoring the asymptotics within each step. And that's an important detail. If you really want to get the asymptotics correct, you can't ignore the amount of computation done within each step. So here are some examples. So addition and subtraction. So the way you compute these is you basically count. Each small number operation, and by small number I mean less than 32 bits, each small number operation on a computer takes, you can imagine taking a bounded amount of time. So if you count the number of small number operations and how that grows with n, then you get the right asymptotic. So we get ON for addition and subtraction, which is not surprising at all. Multiplication this is somewhat of a lie. We're going to be ignoring small factors. A nice one that you might say here is n log log n. But we can do better than that. And this is with the Fourier transform, using the Fourier transform for multiplication. Extended binary GCD. If I asked you the efficiency of the Euclidean algorithm, you would probably say it's linear. But that's the number of steps. And each step, if you're just implementing Euclidean algorithm, is requiring multiplication because you're doing this division process. And so each step is going to have n log n. So you get n times n log n, which is bad. Okay, so that's because that's more than quadratic. And we can get something that's less than quadratic. We can get n log n. So this is with sort of a very tricky approach to it involves a binary GCD and involves sort of what's called a right. So a Euclidean algorithm is O n squared log n, and this is it's using a divide and conquer approach to the binary GCD. Similar to the multiplication approach. Okay, and then there's division with Newton's algorithm. You get log n squared steps. Each step requires 3 multiplications. So you get n log n times another log n. Exponentiation. So Teitelbaum was saying that you have n steps, but each step is taking n log n, so you get n squared log n. And if you're doing modular, if you're doing exponentiation mod of prime, it's still that, pretty much. Point addition on elliptic curves. Without the Koblitz trick. And using the fast Fourier transform, multiplication is the same as ordinary multiplication. With a different constant. And then there's exponentiation. On elliptic curves, which is the same as ordinary exponentiation with a different constant. So I want to compare those. And the other day, it was asked what Scoff's algorithm is, and Scoff at least in terms of how I would implement it, is effectively like that, ignoring some other constants. So, and you can keep going. So, but anyway, the point is, if you do a direct comparison between RSA and Diffie-Hellman and elliptic curve Diffie-Hellman. Okay, let's say you look at RSA 3072 and ECDH 256, which are the same level of security. This is saying that the n we have to use is 3072 times bigger, or is 12 times bigger than the one we use for this. Okay, and if you compare the coefficients of this to this, you get 4 to 15. Okay, so the coefficients are 4 to 15, making, I mean, we're doing simpler calculations if we're just doing ordinary exponentiation. I probably shouldn't be comparing to RSA. I should probably be comparing to Diffie-Hellman, but you're still doing exponentiation in RSA. But you have 4 to 15 as the ratio there. But then, because of this ratio, let the curves catch up. You have that, 4 over 15 times 12 squared, which is then equal to 38.4, asymptotically anyway. So this is sort of estimating that you could get an implementation that was roughly 38.4 times faster with elliptic curves than with RSA. Not saying you could do that exactly. It's just a theoretical estimate based on asymptotics. And so all of these sorts of things need to be taken into account because we expect our information when we're getting things from Amazon to be immediate. We want, and Amazon servers are swamped with this. So they need to be able to do the calculations quickly for however many people are logged in at the same time. So that solves at least part of the problem at the server end, being able to calculate it quickly. Another part is transmission. You need it to be transmitted quickly. And the situation is usually, so with RSA, for 3072 RSA, you're sending 3072 bits. For each exchange. For ECDH, we send 256. We send 256 bits per coordinate. And so this is why there were many attempts early in the history of elliptic curve cryptography to try and reduce the amount of information sent, these so-called point compression algorithms, to attempt to send not the entire y-coordinate, but say just part of the y-coordinate or something like this. What Bernstein pointed out is that you can actually skip sending the y-coordinate completely. You can just send the x-coordinate, at least if you're using the Montgomery curves. You can just send the x-coordinate. And the reason for that, I don't know if you saw this in the notes, but if you read the section about, completely anyway, if you read the section about elliptic curve geometry, I show how on a Montgomery curve you can exponentiate without the y-coordinate. You can basically just use x and z. And but he's saying not only do we do that, we also avoid even checking the y-coordinate, whether we have a valid point on our curve. And as I'll discuss in a minute, that relies on both the elliptic curve and its twist being safe. You need both to be safe and not just one, otherwise Eve has a strong attack. So that is important. Why do you need both to be safe? I guess I should list all of the safety criteria because then I go into discussion about that. So these are the safety criteria. That Bernstein subscribes to and that I subscribe to. Choose a large odd prime P and an elliptic curve E over FP, satisfying all of the following. The largest prime L dividing the order of the elliptic curve over FP is greater than some bound. Okay, with SAGE, you can factor P plus 1 minus AP, okay, and then that factorization could have more than one, will generally have more than one factor. If you want the largest, SAGE lists them in order, so you want the last factor. So you can get the last factor by just minus 1 in brackets. Minus 0 gives you the 0th component of the vector, but minus 1 will give you the last component. And then you don't want the exponent, you want just the prime itself. The exponent should be 1, ideally. You could check that if you want. The attack, that this is the strongest attack against this, that you need to set the bound to resist, is the Pollard row attack, which I am not going to discuss today. It is in the notes. 2, embedding degree. So the way you might want to define this for general number theory versus the way you want to define it for cryptography are slightly different. I'm going to define it for cryptography. The embedding degree, so we want it to be greater than some bound. And you can calculate it as the multiplicative order of P mod L. And I'll explain where that comes from. Okay, and the strongest attack that that's supposed to defend against is the Mauve attack, which I am going to discuss today. I had to pick an attack to discuss. That's it, because that gets me to talk about the Wade pairing. CM discriminant is greater than some bound. Sage, square free part, (4p minus AP squared). You want that to be as big as possible. Attack, unknown. It's basically, Bernstein tries to argue that small CM discriminant could be problematic, but I mean, we don't really have a known attack that makes it that problematic. There's currently no reason to see why small discriminant is any worse than large discriminant. So this seems unnecessarily, if the CM discriminant isn't really a problem, to unnecessarily rule out Koblitz curves, which may indeed be quite safe, seeing as they satisfy the other conditions pretty easily. But more studies should really be exerted to understanding the CM discriminant. So it's definitely a good thing to draw attention to. And I do discuss a little bit my feelings about that in the section of the notes. And there are two more that I list in the notes, two more safety criteria that I'm not going to spend as much time on, except to say that there are ways you can that an attacker can replace a point on the curve you're using by a point not on it, but on some other curve that has weaker security conditions. And if you don't check that that point is on your curve, then you could end up in trouble. So how then can Bernstein say we can get away with not checking the y-coordinate at all? By specifying both that the curve and its twist be safe. So here's the deal. So the NIST curves are not safe if you're not checking that the point's on there for the following reason. So NIST curves are like this. Y squared equals x cubed minus 3x plus b. The amazing thing, and probably the thing that led them to be chosen in the first place, is that the addition law does not depend on b. That's pretty amazing. That would seem to be a great thing. It makes implementation simpler. It makes the algorithms faster. Why wouldn't you want that? Well, if an attacker tampers with B and replaces B with some curve with points of small order and then sends these imposter points to you and you're not checking carefully, you could end up revealing your number mod a bunch of small primes, and then the attacker can weave them together with the Chinese remainder theorem, much like Scope's algorithm, and get your number. And that's basically a polynomial time attack. If you use the NIST curves, you need to check the y-coordinate. You need to check that the point is on your curve. Absolutely. There's no way around it. And so that's the example. Do I have the example number listed here? So I have an example. It's basically the first example I go over in the section. Well, second example. First example is the Diffie-Hellman setup. First example of an attack. Okay, so that's why it either adds a lot more time, a lot more checking that needs to be done to make sure it's safe, or if you want to avoid the checking, you need to use a different curve. So the advantage of Montgomery curves by squared equals x cubed plus ax squared plus x the addition law depends on A, but not on B. So an attacker could send an imposter point from the twist, but if the twist is also safe, they're not going to get very far. Whereas this, there are effectively a much larger number of options for B. We're still working mod P, so there's a finite number of them, but it's likely that quite a few of them will have points of small order. So there's effectively only two options for Montgomery curves, just by changing B to something that is a quadratic non-residue. Whereas here, there's effectively P choices. Well, not quite P. There's going to be some exceptions based on the discriminant. But, nearly proportional to P. A lot more. And so that's a very critical thing. So when you're checking safety of Montgomery curves, you're really checking for both for fixed A and for both B, where B is 1 and some non-residue, not quadratic non-residue. So that is the reason why you need to check both. And it's the first example you can see there. But now, with remaining time, I want to discuss the mob attack and Debye pairing. So, the mob attack is named after the people who came up with it. It uses the Debye pairing, which we will define right now. Debye pairing is a bilinear pairing. It's defined for more than just L, but we're using it for L. From really the elliptic curve isn't dual, but the elliptic curve is self-dual. So two copies of the elliptic curve to the L roots of unity. It's defined on L torsion as I have it here. You can compute it using Miller's algorithm. See example 17. And for an elliptic curve defined over FQ, we need two properties to hold. A, full torsion, full L torsion. B, we need mu L to inject into multiplicative group of some extension of FQ for K as small as possible, which then by basic group order means we need L to divide Q to the K minus 1. i.e. q to the k is congruent to 1 mod L. And so that's why k has to be the order of q mod L. And I am glossing over a little bit here. I mean, technically, to get full L torsion, as you saw in the last lecture that I did, you might need to actually take a quadratic extension. This may be enough to get the L torsion polynomials to split, but if they don't have roots, if the y coordinates, if they aren't squares, if the roots aren't squares, then, well, if you plug them into the polynomial and you get, you might not get points on the curve. So this is kind of a lower bound in that sense. From a theoretical point of view, you might want to define the embedding degree as the least degree extension over which the vapariant is defined. This could be less than that, but if we're trying to be safe, it's okay if we have aim for something less than the degree, the actual embedding degree. If that's as big as possible, then the actual embedding degree is going to be even bigger. So that's not a really big problem. And so the strategy is you set up the vape pairing on the curve, and then you transfer the problem to the multiplicative group, and you can solve in the multiplicative group. Solve DLP in FQK times with index calculus, which is sub-exponential and faster than anything that would work natively on the elliptic curve as it is currently not. So I want to do quickly an example of, I'm not going to do the whole construction of the vape pairing the way I alluded to with Miller's algorithm. You can look at example 17. But I want to, with just a few minutes here remaining, explain how you can use Sage to compute the vape pairing. So, example with Sage. While Alice and Bob are usually successful in their security attempts, Carol and David tend to be people that I pick to be victims of. So here we have David. David is using this supersingular curve over F43. You can check it has embedding degree 2. Right, that's pretty bad for David. P equals 1324 is a base point. With order L equals 11. Right, so you can see 11 does not divide 42, right? But 11 does divide 43 squared minus 1, which is 42 times 44. 11 divides 44, so that shows that it has embedding degree 2. David's key, so his public key, his private key is 6. Compute 6 key equals 45. Okay, so now Eve does not know 6 yet. Eve knows 4, 5, that's PD, and she knows 13, 24. And she wants to extend to full 11 torsion. So I did this calculation by hand, but as I say, I wrote it on this previous page, so I'm not going to write it up again. You can do it mod P, comma L dot multiplicative order parentheses. So that gives you 2. And so then she says, okay, well then I need the extension of, the quadratic extension of F43. So she goes to K dot A equals G F43 squared. And if you want to know, you could ask for the polynomial that's being used here, but you can also just, it's degree 2, right? So you square A, and it's going to output the result 4A plus 9 using the power basis in A. And so then that tells you that x squared minus 4x plus 9 is the polynomial in question, just by computing A squared. So then she defines the elliptic curve E over K. This is all sage stuff. K, comma, 0, 0, 0, 1, 0. And you can check, if you want, that it has order divisible by 11 squared, that it's a abelian group. Actually, it's not something of 11 squared order, but you actually have full torsion. You can do E dot abelian group if you want. To check that, you can do E dot division polynomial. And E actually needs points to work with. So she computes the division polynomial. It splits. She needs the first, since she does not have full 11 torsion over F43, she needs the first factor which with a root in the extension, but not in the base field. So that factor, at least on Sage, is this. If you do it on Magma, you might get a different factor. I don't know. But that's giving you the x-coordinate. So then you can determine the y-coordinate by doing E dot defining polynomial, which gives you, say, x cubed plus x minus y squared. Well, it includes z, actually. It gives you the homogeneous polynomial. And so you plug in with minus 2a plus 4, and z equals 1. And you're left with a quadratic in y, which you then factor. And it gives you